Good morning, namaste, Huan Ying, greetings of the day to you. If you can hear me, please smash that chat button. Let me know that I'm coming in loud and clear. All right, I hope everyone is doing well. Thank you for letting me know. Hello. Let me show you the responses from the week 1 poll. 22 people are awesome, 65 people are good, 2 people bad, 7 people, please, I want to die. Hopefully we can move those people into the good and awesome category. So thank you for joining me today. I do hope that you're having a good day and a good week. If you don't know who I am, I'm the lecturer for the calculus part. I'm Chris, and I'm a professor. Some of you maybe met me on Monday, but if you didn't, hello. In today's lecture, we're going to continue our journey into calculus. And one of the nice things about the calculus in this course is some of it will be familiar to you and some of it's new. So today the ideas may be quite familiar to you, but they're important, and we're still in the introductory stage. Okay, so nothing too crazy today. All right, so let me share my screen with you and we can begin. Okay, so this is what we do. I usually go through the notes and, just with a pen, and you can just follow along. And I'm recording this session, so you can just sit back, relax, raise some questions in the chat if you want to, and I'm happy to take questions. And if something's unclear, just let me know. All right. So in today's class, we're going to continue our calculus lectures, and we're talking about limits of functions as we approach infinity. Okay, so Eddie, I can see your hand up. I'm just going to lower it. If you have a question, just make sure you put it in the chat, or you can ask me at the end. All right, so we're going to look at the following ideas today, still quite introductory. So why do we need limits and these so-called indeterminate forms? Now, the indeterminate forms are really interesting, right? So you have these weird things like infinity over infinity, or infinity minus infinity, or 0 times infinity. These are all special indeterminate forms, okay? And they arise when you take limits of functions. Okay, so we'll be looking at these kinds of things and trying to work out what they mean. Okay. All right. Okay, so we'll do some examples involving the limits as the input goes off and becomes very large and positive. And we'll also talk about some of the motivation and also these indeterminate forms. Okay, so a big picture type of idea first. There is no calculus without limits. Okay, so the limit is a fundamental concept. It is the absolute fundamental concept of calculus. Okay, it is actually impossible to talk about calculus without limits. Okay, now some, some people try, but it's absolutely not possible. So in order to really understand and work with calculus, you really need limits. You really need limits. Now, we don't always use limits every time we differentiate something or integrate something. Let me go back to my big head here. So if you've done calculus before, which you should have, when you differentiate something, you don't always use a limit. And when you integrate something, you don't always use a limit, right? So limits are important, but we don't use them every day, but they're still super important, okay? So this is what we're going to look at today. All right, so just to refresh our memory on limits, okay? Limits help us to answer the following question. How does the graph of a function behave as its inputs, x, vary in some particular way? And in our case, we're going to look at the case when x, the input, gets large and positive, or as x approaches infinity. All right? So this means x approaches infinity. Okay? And the answer that we produce in these kinds of situations is what y value is the function approaching as x gets large and positive. Okay, so what y value does the function approach? Now I'll show you some pictures in a minute, but that is the fundamental question. Okay, and these kind of questions, like I said before, they can be used with bigger ideas like differentiation, integration, summation, these sorts of things. Okay. All right. Okay, so what do limits look like? Well, I am glad you asked. Abdul Rahman, I'm looking at your question in the chat. Similar to numerical analysis, we won't really do any numerical analysis in this lecture, but sometimes in numerical analysis, you want to approximate something and you take a limit. So I'm sure there are some connections there. Okay, so let me show you some notation and then we can, I'll show you some examples, right? So what these things actually look like, all right? So in this lecture, we're going to look at a function and work out what happens to the function as x becomes large and positive. Does the function approach a particular value? And if so, what is the value? Okay. So the notation, when you're doing these kind of questions, this is the kind of notation you'll see. Okay. So when we write this, L is a number. Okay. F is a given function and x is approaching positive infinity. Okay, so a basic definition for this notation means that as the input x becomes large and positive, the graph of x approaches the horizontal line y equals L. So let me draw you a picture and we can show that, and then I'll show you some GeoGebra. Okay, so suppose I've got a function like this. Okay, that's the graph of the function. And as the input gets large and positive, the graph is sort of flattening out and you've got a let's say an asymptote here. Okay. In this graph, as x gets large and positive, the graph is approaching this horizontal line, y equals L. Okay, that's one simple example. Let me give you another one. Okay, and then I'll do some GeoGebra. Here's another graph that we might have. It might look like this. Okay, you can see in this graph, the function is kind of wrapping itself around the x-axis. Okay, and it's getting closer and closer and closer. So in this case, the limit as x gets large and positive would just be 0, because that's 0 on the y-axis. Okay. Daniel, that's a good question. Let me have a look at your message in the chat. Does L always have to be a number? Look, L's not going to be a function, right? It's going to be a number, or it's going to be positive or negative infinity. Okay, so you could have a situation where the graph is just increasing and it goes off to positive infinity. Then it's not possible to draw a horizontal line y equals infinity, right? So yeah, so it's a constant function, as Aidan said. These sort of horizontal lines are still a constant function, but you're not going to get a function depending on x. Okay. All right, let me show you some pictures on GeoGebra, and we can have a look. So definitely keep those questions coming. All right, so here's an example of a function there, okay? And you can see, well, the function bobbles up and then decreases, but it looks like it's approaching some kind of horizontal line. So if I put in, let's say 1/3, okay, it's a bit hard to see from the graph, but actually what's happening is this green curve is actually, it has this asymptote 1/3. Okay, so if I go all the way out there, then I'm going to approach that horizontal asymptote. Okay, here's another one. This is a different kind of function. Okay, as x gets very large and positive, this graph is just going off to positive infinity. Okay, here's another one. Okay, this graph looks like it's decreasing and it's getting dragged down to 0 as we move off to the right. Okay, here's another graph. This is this thing here. So it sort of moves around, but as x increases, you can actually see, well, that function there has this horizontal asymptote y equals 3. So the limit of that function would be 3. Okay, this one, it's just decreasing down towards 0. So the limit of that function would be 0 as x gets large and positive. This one, well, that looks like it's approaching something. Okay, if I put in 1 there, it actually looks like it's approaching 1. Okay, so one of the nice things that that you have at your disposal is graphing software. So whether it's GeoGebra or Maple, Mobius, something like that, you'll be able to plot these graphs pretty easily. Okay, now in today's class, we're going to look at algebraic techniques, really simple algebraic techniques. Okay, but the basic idea so far is as x gets large and positive, what is the y value doing? Is it approaching something? And if so, what is it? All right. Yes, Abdul Rahman, we can approach negative infinity. Let me show you something about that. So instead of approaching positive infinity here, you could also approach negative infinity. So instead of going all the way out here and seeing what the graph is doing, you go all the way out there and see what the graph is doing. Okay, so you definitely can do that. That's a really good question. Okay, let's do some examples. Now, I just showed you this example on GeoGebra, but let's just do it algebraically, because I think that's probably the ideas that you're probably most familiar with. And so the strategy is to use algebra to simplify. Okay. All right. Max is asking a question on the chat. Do we ever talk about limits as y approaches something? Well, Max, we sort of have y equals f of x, yeah? They're the functions that we look at. And x is, sorry, let me move that down. And x is the independent variable. So you vary that and that varies, okay? You might be able to do it the other way around, but it's not common in this course. All right. So Steve is on the chat with some strategies already for this one. With these kinds of problems, the top goes to infinity and the bottom goes to infinity. So there's a battle going on between the numerator and the denominator. So who will win? Let's look at Steve's suggestion. One of the strategies here is to divide top and bottom by the highest power. Of x in the denominator. Okay, so everyone has already piped up, and I'm just going to use the function and divide the top by x squared and the bottom by x squared. So I can just take this, divide it into there, divide it into there, divide it into there, divide that into there, and so on. Okay, so you're going to get 12 minus 2x squared plus 1 on x squared. And down here, we're going to get 4 plus 1 on x squared. Now, the nice thing about this form is that, well, if we put x approaching infinity in here, this is going to be different. Oh, 2 on x, sorry. Yep. So that goes into there, 2 on x. Thank you. So that's 2 on x. So this will go to 0 as x gets large and positive, because 1 on x squared goes to 0. This will go to 0, and this will go to 0. Okay? So the limit of our function, we take the limit of the top, that's going to be 12. The bottom's going to be 4. Okay. So in this case, it was exactly like our picture from GeoGebra before. This limit, there's a battle between the top and the bottom, and it's a tie. Okay, we get this basic limit. So let me just share that with you again on GeoGebra, because I think it's an important example. Okay, so here's our function, and here's the horizontal line, y equals 3. Okay. So there it is. Okay. So in this case, the limit is just a finite number, and it turns out to be positive 3. And the way we did that was to simplify the expression and then take the limit. Okay, so yeah, Alberto, factorizing is not great in this case. Sometimes it is, and you can cancel things off, but in this case, we just looked for the highest power in the denominator and divided top and bottom. Okay. Yep, you might, yeah, Abdul Rahman, you might be able to do long division, not a problem, but I think this is actually a faster way. Okay, if you want to divide that into that via long division, well, of course you could do that, but yeah, I think that would slow you down a bit. Okay, a couple of more examples. So when I write this notation, of course, I mean the limit of the whole thing. Okay, so sometimes you put the brackets in, sometimes not. Okay, so let's look at the first case. This is not a difficult problem, but let's just refresh our memory. Okay, so there's no x's in the top, so the 7's going to stay the same. And there's an x squared plus 1 in the denominator. Now, x is getting large. So as x gets large, x squared plus 1 will also get very large. Yeah? So if I'm taking 7 and I'm dividing it by a very, very large number, this, of course, will go to 0, as people are saying, right? So let me just put that up. I'll put that up on GeoGebra in a second. Okay, so basically you've got a finite number divided by a huge number, and that's going to pull that down towards 0. Okay. Let me just put that onto GeoGebra. So let me just switch over. Okay, so here you can see that's the curve. Oh, hang on, it should be squared there. Let me fix that up. Okay, that's better. And so you can see as we move over, x gets large and positive, the graph is decreasing down towards 0. Okay. And for the next one, what do you think is going to happen for this 6x squared plus 5? As x gets large and positive. Yes, absolutely. Carl and Advaita and Masatomo, thank you. So for part B, this is basically just a parabola. Okay, and if we head out this way, right, and keep going out that way, the graph is just increasing and increasing and increasing. Okay, so for this one, okay, so obviously not a number. We can't draw a horizontal line y equals infinity, but it's just increasing and increasing and increasing. Okay, off towards positive infinity. Sometimes they'll increase off to negative infinity. That's okay too. You would just have negative infinity here. Ah, Daniel, that's a good question. What is the difference between the limit does not exist and the limit is infinity? Let me give that the big thumbs up. Good question. Best question today so far. So the best way I can explain that is through some simple examples. Okay, so let me go back to GeoGebra, and I've got a couple of examples ready for you. Okay. All right. So let's put in sine x. Now that is a curve where it obviously doesn't go to infinity, right? Or negative infinity, but it doesn't approach a limit either because you can't draw that horizontal line. It just goes up and down and up and down and up and down. Okay, so the limit doesn't exist there. Okay, let me give you another one. That one. Are you ready? Ooh, it's a bit spacey. Okay. In that example, the graph doesn't go to positive infinity and it doesn't go to negative infinity. And there's no horizontal line that you can draw. So that limit doesn't exist either. Okay. But something like that, that definitely goes off to positive infinity. Okay. Well, Abdul Rahman, a function cannot have two limits. Oh my goodness, that's a really, hang on, I got to acknowledge that too with my big fat head. A limit, there's only one limit. Okay. The situation is the limit, there's a finite limit, right? Or the limit doesn't exist, or the limit is infinity or negative infinity. Okay, so there's only, you can't have a function with two limits. It's just not possible. Okay, that is a great question too. Okay, so let me go back to my document camera. I'm loving the questions in the chat. So these were two really simple examples. Let me keep going. We're going to make it a little bit more challenging now through these indeterminate forms. Okay, so it's a little bit weird when people see these kind of problems, and they usually arise when you take a limit in the limits or in the limit questions. Okay, so all of these kinds of forms are called indeterminate forms. Okay, and there's no way of understanding these without extra work. Okay, so you need more analysis. Okay, there's no way of understanding these forms without doing more analysis or more digging, right? Okay. All right. So they're called indeterminate forms, and they have no meaning on their own. Okay, and we're going to look at some techniques to make sense of them. Okay, so let me give you an example here. Something like this. Okay, let's say that's my function, and you want to work out what happens as x gets large and positive. Now, the problem is the top goes to infinity, the bottom goes to infinity, so you've got this infinity war, right? And some of you will see the top increases faster than the bottom. That's important, but you still get this indeterminate form. Okay, so infinity over infinity, you don't know what it is. It could be 1, it could be 0, it could be something else. Okay, what we need are some techniques. Yeah, Steve, we'll look at L'Hopital's rule later, but we're just going to use algebra for today's lesson. Okay. All right. So let's have a look at these types of examples. And in fact, it kind of, you've got a similar situation here. The top function, which is a parabola, goes to positive infinity, and the bottom function goes to infinity. So you've got this infinity war between two. Love it, Alberto. Avengers. I should get some Avengers in the background. Okay, so how do you do it? Well, one technique. Okay, this is sort of your infinity over infinity. Again, look for the highest power in the denominator and divide top and bottom, just like we did over here. Okay, the highest power in the denominator was x squared. Divide the top and bottom and see what happens. Okay. All right. So let's do that. So I'm going to divide top and bottom by that. This is going to become 6 on x. So you can see what's happening here as x gets large and positive, that's going to go to 0. That's going to go to 0. What's going to happen down here? Okay, that's going to stay as 1 and that's going to go to 0. So you're going to get 0 on the top and 1 on the bottom. Exactly. Shub, you're on the right track there. So let me see if I can squeeze this in. Okay, that's going to be 0 plus 0 over 1 plus 0. And 0 over 1 is just 0. Okay, so all we really did there was a little bit of algebraic construction. Yes, Daniel, you're right. Like here what we're sort of forcing the denominator to be a finite number, and not 0, of course, as well. Okay. All right, so let's do the second one. The highest power in the denominator is x squared, and there's an x squared up the top, so there's a battle. There's a battle here. So let's do that. Okay, so that the top's going to become 6. The bottom is going to become 1 plus 17 on x squared. So what's going to happen now? This is going to, that's going to stay the same. That's going to go to 0. That will be 1. Okay, so 6 on the top, 1 there, 0 there, equals 6. Okay, so yes, so everybody, Nelufur and Ace, thank you. So we get 6 there. And finally, what's going to happen with the last one? Who can suggest what might happen? There's a battle again, x squared on the bottom, x cubed on the top. What do you think is going to happen? Yeah, the numerator is going to grow, and this is the whole thing is going to go to positive infinity. Okay, so let's do that. So we've got negative 6x cubed over x squared, and we've got x squared plus 17, and I'll just divide x squared into that down here. So here on the top, I've got 6x for 1, and I'm going to get 1 plus 17 over x squared. So what happens to this as x gets large and positive? Well, this is going to go to 0. That will be 1, and this is going to go off to infinity, negative infinity, right? So that's going to go off to 1, and the top, as x gets large and positive, negative 6 times that will be negative infinity. Okay. Correct, Ronan. Yeah, we've still got that. We haven't been able to manage that away. So we find down here, but we haven't been able to manage that away. So that's still going to grow really, really quickly towards negative infinity. So these are the sort of tricks and the strategies that you can use in solving these kinds of problems. And they're mostly algebraic. Okay. Let's have a look at the graph. Yeah, Azalea. Let's have a look. Let me have a look. I'll just put it into GeoGebra here, and I'll show you in a second. X squared plus 17. It's a really good suggestion. All right, so let me just show you what it looks like with GeoGebra. Okay, so here is the graph of the function, and you can see as x gets large and positive, this graph is just heading off towards negative infinity. Okay, so basically the x cubed wins the battle, or the negative 6x cubed wins the battle, and yeah, it grows much faster than the denominator. Okay. Snaya, just check you're working. If you're dividing by x cubed, I wouldn't divide by x cubed, because one of the things that we are concerned with in our strategy is looking at the highest power in the denominator. Okay, so yeah, it's just, you just got to check you're working on that one. Okay. All right, so let's look at a slightly more complicated example. It's a really good question. So here's one that I'll show you in a second. So I'll get rid of that one. Let me just pull that down. All right, so this is actually the next question in the notes. So we want to take the limit of this function as x becomes large and positive, right? And so you can see from the graph that the function looks like it's approaching 0 as x gets large and positive. So that's one way of understanding it. There's also an algebraic way of understanding it that I wanted to share with you. Okay, so I always try to draw pictures first, and then worry about things like algebra and stuff later. So this is a classic example, and the strategy here, at least in my opinion, is to multiply by a factor of 1. Okay, so what do I mean by that? You're basically multiplying your function by something where it's going to simplify the expression. Okay, so this is one of those questions where a lot of people don't know where to start, but once you know the strategy, you can use it a lot. Okay, so I'm going to multiply by this. Now, I'm going to have a similar form to our function, except I'm going to have a plus here. And because I don't want to change the function, I want to multiply by a factor of 1, I have the same thing here and the same thing here. Now, you may look at that and go, let me go back to my big head. Chris, what's going on? You're making it much more complicated. Well, we go through this extra step to go from the complicated to the very, very simple. Okay, so we're going to a good spot. We're going to a good place. All right. So if I expand this out, you'll see what I'll get. We're going to get that times that, that times that, that. You've got essentially some cancellation. Okay, so just doing the algebra. And that cancels with that. So if we want to take the limit of this mess, we can actually transform it and take the limit of this. Okay, so let's call this L. Okay, and we already sort of know that this is going to be 0 from our pictures, but let's do it. As x gets large and positive, we're going to have a very large denominator, right? Because this is going to be large and positive, and this is going to be large and positive. So what is our limit going to be? 1 divided by a very large number, which is just 0. So yes, we are rationalizing in your complex numbers part of this course. You'll see a lot of this going on. You're actually multiplying by a factor of 1 that involves the conjugate. So the same thing, you're just changing the sign here. Okay. So Masatamo, it's a good question. You might be able to do other techniques, like trying to divide out the x squared, top and bottom, those sort of things. But I just wanted to show you this strategy because it's a very useful one. And if you don't know the strategy, then it's hard to know where to start. Okay. What else have we got? We've got a couple of more examples. These are a bit more difficult now. Okay, so let's look at those, and then we can attempt them. I'll show you a picture, and we can look at them on our graphing software. Okay, so here is the function. You can see as x becomes large and positive, the function's decreasing down towards 0. So we would expect our limit as x gets large and positive, as x tends to infinity, to be 0, right? So how can we do that? How can we sort of justify that? Well, the denominator is growing very fast, much faster than the numerator. Okay. So let me do that. And the other one is here. I think that's the one. Okay, so that's the second part of this question. So you can see it looks like there's going to be some sort of limit there. It turns out that it's going to be 1/3. So let's do this, and we can do them algebraically and see what happens. Okay, so for the first one, I'm going to use the same technique as before. The highest power in the denominator is x squared. So I'm going to divide top and bottom by x squared. Okay, so that's going to give you 1 on x. Down the bottom, I'm going to get 1 plus 1 on x. Now what's happening to the top as x gets large and positive? That goes to 0. This also goes to 0, we're going to have techniques to like actually prove that, but I'll just state it now. The reason is x squared grows larger than sine x. Sine x just goes between -1 and 1. Okay, so that gets dragged down. So that goes to 0, that goes to 0, that goes to 0, and that goes to 1. Okay. So that's 0, that's 0, that's 0. Okay. So don't worry too much about why this goes to 0. You can obviously draw a picture with graphing software, but we will show like rigorously why this goes to 0 in another lecture. Okay. Yeah, sine x is bounded between -1 and +1, Daniel. So basically x squared drags this function down towards 0. Second part of the question, let's just do the division here by the exponentials, okay? The exponentials grow much faster than x squared. So if I divide that into the top and the bottom, I'll get something like that. Okay? And so that goes to 0, that goes to 0, and the rest is untouched. Okay? So the idea there is that exponentials grow super fast, and they grow faster than any power function. Okay, so I've just sort of done the algebra there, dividing top and bottom by not the highest power here, but the function that grows the fastest. All right. So you can see, look at the denominator, find the either highest power or the function that grows the fastest, and then divide that into the top and the bottom. Okay, that's a really easy strategy. Okay. Yeah, Abdul Rahman. So e to the x grows faster than x to the n. Okay, so x squared, x cubed, x to the power 4. So this thing goes to 0 because the e to the x drags the x squared down. There's a battle between the e to the x and the x squared, and the e to the x wins. Okay? Theo, it's a good question. It's still the same. Okay? So for any power, e to the x grows much faster than any power. Really good question, though. All right. Last page. We already looked at an example of this. It does not exist. Okay? It oscillates. Okay? So with a function like sine x or cos x, it doesn't have a limit. Okay? For part B, you've got something like this. And again, cosine oscillates between +1 and -1, and e to the x drags it down. Okay, so for this one, this is growing, the denominator is growing super fast, and this is just oscillating between +1 and 1. So for that limit, you're absolutely right, Shub. It's going to go to 0. And finally, what about this one? This one's a bit of an interesting question. What happens with this? Can anyone suggest in the chat what the limit of this crazy looking thing might be? Okay. So people are putting in 1, which is correct. Let's see how we might do it. Okay. So this is another strategy, and this is the final one that I'll leave you with. Okay, I'm going to introduce some notation. I'll let L be this limit, and I'm going to consider the natural logarithm of both sides. And the reason why I'm going to do that is to manage away this exponential. So this ln here is natural logarithm. Okay, so what I can do is take this out the front. And we have something like this. So this, you can use your log laws. This comes to the front. Log of E is just 1. Okay. This is going to go to 0. So we know that the natural logarithm of the limit is 0. So if you just solve that, you know that the value of the limit must be 1. Okay, that's quite a difficult question, but the important thing is the strategy, right? If you have some weird looking function or some weird looking limit, you can take the natural logarithm, or you can exponentiate it, do some things to it, and get what you want. Okay. All right. So yes, another good example there, Ricardo. You can also shift the limit into. So this is a really good suggestion, Ricardo. You can also shift the limit into the exponent, which is probably a faster way to do it, right? So that is also another way of doing it. Okay, instead of having the limit down there, you can shift it up into the exponent, which I think is really good too. Okay. All right, folks, thank you so much. Hopefully everyone's feeling good. And yeah, Captain Bill is here, the lecturer for algebra. So as you know, we have 2 hours together. 1 hour is calculus and then algebra, or algebra and then calculus. Okay, so thanks for the chat today, everyone. I really enjoyed the questions, and yeah, just enjoy the day wherever you are. And let me know in the chat if you have questions. I'll hang around for a couple more minutes. Most important thing, of course, get onto Mobius. Get familiar with the Moodle webpage, and I have a tutorial today at 2 o'clock and 4 o'clock Sydney time. So if you want to come, please come. Okay. All right. I'll sign off, everyone. Namaste. Thank you. Ibrahim. Yeah. I can't remember. Someone gave it to me. Actually, my kids are into Mario and stuff. So next week I'll probably have some other plushies, but people seem to really like them. I'll see if I can find out. All right. Take a break, and I'll hand over to Bill when he's ready. Daniel, are the tutorials covering the same content but at 3 different times? Yes and no is my answer. Sometimes you'll get a question that's repeated, but Other times the tutors will do different questions. I think it's really up to you as a person in the tutorial to ask for what you want. Maybe you want them to do a specific question, or maybe you want them to explain a bit more about limits. It's up to you, okay? My suggestion is just to try some tutorials and see what works for you, okay? Practicante, the Mobius is due Monday afternoon, local Sydney time. I think it's 1 p.m. in the afternoon. So that's when you need to submit it. Yeah, Starry Night. Yeah, it's pretty cool. I'm feeling very blue today. My room's very blue. Thanks, Steve. All right. I'm heading out. Have a great day.